Hi, my name is Martin Danellgan and I will present discriminative appearance-based tracking and segmentation. So a brief outline of this talk, I will actually start by looking back and look at what we learned from correlation-based visual tracking. Then we'll directly get into quite new stuff, looking at end-to-end discriminative visual tracking. Then we'll go on to robust video object segmentation. And finally, we'll look at our recent work on how to deal with distractors in tracking. So visual tracking, of course, comes in very many different forms. You can track feature points, you can do multi-object tracking, or track completely arbitrary objects like here. So I will mostly cover the latter, where the target we want to track is given to us in an initial frame by, for instance, a bounding box. So why would we like to do appearance-based tracking? First of all, we cannot model or categorize everything in the world, and especially we cannot learn the detectors for them. So we also want to be able to track unknown or unmodeled objects. This is of course also important in drone applications, where we might encounter all different kinds of objects. However, appearance-based tracking might also allow us to track us more accurately and faster because we're using the actual appearance of the target that we want to track. But we're also learning an explicit appearance model of the target, so we can also use it to re-identify, which is important in many applications. And these latter two things allows us to combine appearance-based generic tracking with class-based multi-object tracking to even further improve performance. So appearance-based tracking comes with a number of challenges. First of all, as I said, we want to be able to track any kind of object, so this leads to a generalization problem. We're also only given a single initial example that defines the objects that we want to track. So here we have a limited data problem. Appearance, of course, also changes over time. So we need to do online learning. And finally, if we want to develop end-to-end approaches that does tracking, we also need to learn this online learning mechanism. So meta-learning naturally arises here. Okay, so let's start with a simple discriminative tracking pipeline. So we have the object that we want to track. The goal now is to train a classifier to categorize object patches from negative patches from the background. Given a new frame in the video, we can then apply our classifier and update the location of the object according to the highest confidence score. We could then use this bounding box to further update our classifier. So the question now is how to learn this classifier F. It needs to be robust, adaptable, and also fast, so we can do online tracking. So first I will talk about discriminative correlation filters. So for those who don't know, they really dominated the visual tracking field from roughly 2013 to 2018. So the first question is, why did they become so popular? Well, they were good, fast, very simple, and also flexible and easy to build upon. And actually they are still popular in UAV and drone-based tracking today because of these properties. So let me give a brief introduction to the DCF formulation. So we start from a set of training samples containing the target itself and some surrounding background. From these training samples we extract some multidimensional features. It could be deep features, but it could also be hog or some classical feature. So the idea is then to train a convolution operation that takes the feature map as input and then return a confidence score that indicates the object. To learn our filter, we minimize a least squares discriminative loss. So here y is our annotated confidence scores, which indicates the target location, and we also have some weights. So the core idea in the CF-based tracking mainly comes in to the optimization of this objective, namely that we should apply the discrete Fourier transform to it. So this allows us to reformulate the loss like this. From here we can further derive the set of normal equations. Now, what the DFT does is to sparsify or even diagonalize this equation system. And this allows us to apply efficient direct solvers or more efficient iterative methods like the conjugate gradient. So this formulation formed the basis of a number of our works going back to 2015. But next, let's discuss the problems of this DCF formulation. So for example, we can look at the UPDT, which was really the last of our pure correlation-based trackers. And as you can see, the quality of the estimated bounding box are not particularly good. This was the motivation for the first work that I will present, which is ATOM. So how can we predict accurate bounding boxes in visual tracking? As we more know now, bounding box regression is actually a quite complex task that requires high-level knowledge and understanding about the objects. So we cannot really learn this from only a single image. But the challenges here is that the target class is unknown, so we cannot also rely on class information. Further, we need to generalize to unseen classes. So therefore, we need to integrate target-specific information. In ATOM, we propose a bounding box regression approach based on IOUNet. So it's trained to predict the IOU between a given bounding box and the real object. And during inference, we can maximize this value with respect to the bounding box in order to fit a very accurate bounding box around the target. So already this gives us a fair improvement over a multi-scale estimation baseline. But in tracking, we also want to integrate information from the target itself, which is given in the reference frame. So for this, we proposed a modulation-based method where we conditioned the IOU prediction network on the reference frame. And this gave us a further significant improvement. So more relevant for this talk, we also completely redesigned the classification component in ATOM. So here we considered a classifier consisting of two convolutional layers which we want to learn online during tracking. And this we do again given a discriminative least squares objective. The question now is how can we optimize this objective online? So for this we implemented a very efficient online optimization algorithm based on Gauss-Newton and conjugate gradients. And the key thing here is that we could implement this using only differentiable programming, so basically using backprop. If we compare this with gradient descent, we see both much faster convergence in the loss itself, but also better final tracking performance. The final tracking pipeline then looks roughly like this. So first we apply the classifier, which gives us an initial target location. We then generate an initial box and refine it using the bounding box estimation module based on maximizing the IOU. And finally, we use this box to further update the classifier. I won't go into details into results, but at the time we had state-of-the-art performance and at a very reasonable frame rate. So let's look at what discriminative correlation filters gave us that also persisted in this work. So first of all, it's the idea of having a convolutional discriminative classifier that is also learned online. So this we used, as you saw in ATOM, and will continue to use in the subsequent work I will present here. The second is the optimization method itself. So in fact, the optimization method I presented in ATOM is heavily inspired from CCOT and ECHO, where we also used conjugate gradient. The key difference here was that we could implement a completely generic algorithm using differentiable programming that is given to us in frameworks like PyTorch and TensorFlow. So the next question then is, why didn't we use the Fourier transform here to optimize the classifier? And the answer is quite simple. There's no computational benefit of using this if you have small kernels. So when we're working in a quite low resolution deep feature space, we have a quite small classifier kernel. We don't anymore have a benefit of using the Fourier transform. And by not using the Fourier transform, we also completely avoid this issue with the boundary problem that, although inspired a lot of research in the DCF domain, we would prefer not to deal with. So the main disadvantage of Atom is actually that it's not fully end-to-end. While we trained the bounding box estimation, we couldn't train the full tracker because we didn't backpropagate through the optimization method itself. So this is the key problem that we address in the next work, learning discriminative model prediction for tracking. So here, let's start with a general tracking pipeline. So again, from the reference frame, we first extract some features. Then we want to use these features along with the bounding box annotation to learn a representation of the target that we want to track. So the module that does this, we call the online learner here, and it can, for instance, output the parameters of a classifier. Then we want to apply this classifier on the next test frame where we want to locate the target. So the question is now, what properties this online learner should have? Of course, it should be robust and fast, but we also want to train this full system on annotated datasets where we need to backpropagate the loss of the final classifier score. So we also need this module to be differentiable. So a very popular architecture is Siamese networks. So here we first crop out the target region and extract features from there. And these features, or this template, is then simply convolved with features extracted from the test frame. So surely this operation is differentiable and very fast. The question now, is it also robust? And in fact, Siamese trackers are not very robust to, or especially when you have similar objects in the background of your video. And the reason for that is really that we completely disregard the background in the reference frame. So this cropping operation only keeps the target appearance while we completely disregard very valuable information in the background that might also contain the distractor objects. So in this work we propose the dim tracker. First of all, we use a full set of reference frames, so we're not necessarily constrained to a single reference image. Then we first extract some features from them. These are then fed into the model initializer, and this module works similarly to the Siamese trackers and only uses the target appearance. However, this only serves as an initialization to our main component, which is the optimizer module, which then refines this prediction using the full reference set, also including background information. The output of this module is some weights for a convolutional layer, which we then apply to future test frames in order to localize the target by classifying them. And as we will see, this module is both fast, differentiable, and robust. So first of all, let's take a closer look at this model optimizer. The model optimizer minimizes the following loss. So we have our filter weights F that are applied to our training samples X, which have the annotations C here. And this residual function measures the discrepancy between the predicted target confidence scores and some label Y here. So in the simplest case, we can just take the difference of these two. What we do in practice is to create a somewhat more robust version inspired by the hinge loss, but I won't go into the details of this here. The question is now, how can we optimize this objective fast to ensure real-time tracking? An optimization algorithm, all of you know, of course, is simple gradient descent. But we have a very constrained special objective here, so we can do much better than just gradient descent. But we don't want to make our optimization algorithm too complex, because remember, we want to integrate this as a layer in our neural network, and we want to be able to differentiate through it. So a very simple thing we can do that is still incredibly effective is steepest descent. So here we calculate the optimal step length in the gradient direction. And by applying a Gauss-Newton approximation, quadratic approximation of this objective, we can derive the optimal step length according to this simple formula that is also very easy to implement. Then we can perform end-to-end training of our full architecture. So during training we sample a reference set and a test set, and these are just fed into our network as follows. And we apply a final loss on our predicted classification scores on the test set. So here we first evaluate the impact of our optimizer. So no optimizer here only means the initializer module, which corresponds to a Siamese baseline. So as you see, our discriminative optimizer, or optimizer solving a discriminative objective, gives a very large boost in performance. We also observe that end-to-end training, which we couldn't do in the atom tracker, is in fact extremely helpful. So again, at the time we achieved state-of-the-art results, and particularly interesting was the results on the Lasot dataset, which contains very challenging and long-term sequences. Next I will present two works that develops an approach for probabilistic regression with applications to visual tracking and detection and other tasks. So while I have talked a lot about classification, if we think of it, tracking is really a regression problem. So first of all, what I called target classification before is really regressing the center of the target object. So we can call this target center regression. And as I presented in Atom, we also want to do accurate bounding box regression. So already in the DIMP tracker, we have two types of regression problems. So a more general question in machine learning is how we can best do regression. So what you're probably most familiar with is what we would call direct regression. So here we directly learn a mapping f from the input space to the output y. So an example that is of course very relevant for us in tracking and detection is bounding box regression. So here x represents an image and y is a bounding box. Our approach is instead to predict a distribution over the output space y given the input image x. And one of the advantages of this is that now we can actually capture uncertainty in the output. We parameterize our distribution using an energy-based models as follows. So this means that our network takes as input both the image x and the bounding box y and outputs an energy value s. Then to train our energy-based model, we minimize the KL divergence between our parameterized distribution and the label noise here. Note that we always have different degrees of label uncertainty in our regression applications, and here we identified two different sources of uncertainty. One is annotation noise, that is simply due to inaccurate or noisy annotations, as in here. The other one is task ambiguity, that tasks such as target center regression is often ill-defined. Okay, back to our loss function. So now, how can we minimize this? We first simplified the KL divergence loss as follows, splitting it into two terms by using the definition of the KL divergence and the energy-based model. We then propose two different methods to approximate and minimize this objective in practice. The first is grid sampling, where we simply sample the objective in a grid, and this is really perfect for 2D coordinate regression task For instance, when we want to regress the center of the target in tracking. And next is importance sampling. So specifically, we approximate both integrals by sampling from a proposal distribution Q here. And we use this formulation for bounding box regression. For inference, we then compute the most likely output value y star here. And note that for doing that, we don't have to compute the normalizing constant of the energy-based model. We simply have to compute the maximum of the energy function. And similar to the IUUNet approach that I presented earlier, we use a gradient-based maximization strategy here. So in these two papers, we evaluated our approach on 4 tasks in total. So for instance, on tracking, we achieved a very large improvement over our baseline DIMP method that I presented earlier. But we also tried detection using a faster RCNN baseline, age estimation, and head post estimation. So in the DIMP tracker that I presented before, we saw how we could develop an optimization-based neural network module that internally minimizes a discriminative objective. So next I will talk about how we can generalize this concept. And we will do this for video object segmentation in this work, Learning What to Learn, that we presented in ECCE last year. So different from tracking, in video object segmentation, we're given an initial mask of the object, and we then want to segment the object in each frame of the video. So let's design a first approach based on the DIMP tracker architecture. So we have our reference frame and annotated segmentation mask for this frame. So first we extract some deep features. Then we want to online learn the weights of a single convolutional layer that outputs the final predicted mask. So again, we do this with an online learner. So here we minimize the difference between the predicted mask obtained by one convolutional layer and the annotated mask y. So we do this by minimizing a similar least squares objective in this case. Now on the test frame, we first extract features again. Then we apply our learned convolutional weights to give us the final segmentation result. Now the problem here is that we're learning and applying this convolutional layer in very low resolution or on very low resolution deep feature maps. So the output segmentation scores won't be very accurate. It only acts as a very coarse segmentation mask or guide. So what we can do in this case is to input this coarse segmentation into a convolutional decoder that also uses low resolution feature maps to and learned segmentation priors to output the final very accurate segmentation. So note that our convolution layer here now in fact is an internal network module. This means that we are not constrained to a single channel output. So why not learn several convolution filters that produce a multi-channel output that encodes the final segmentation mask? The question now is how we can learn all these filters. So let's go back to the reference frame for that. Instead of a single channel mask, we now want to predict a multidimensional mask encoding. So what should be the labels for that? Or in other words, in our loss formulation, what should replace our y? What should be our target value? So the answer that we propose in this paper is that we can actually learn what these labels should be. Okay, so let's look at how we do this in detail. So given the annotated segmentation mask, we feed it into a label generator that is learnable and produces a multidimensional mask encoding. And it is this mask encoding that is then fed into our online learner module. In our loss formulation, this corresponds to adding a network E here that predicts the labels from the mask Y. We can further improve upon this formulation by adding a weight predictor W here. So it also takes the masks as input and predict a set of weights for each channel and each spatial location. So what this can do is to assign higher weight, for instance, for the target region or for more certain regions, while it gives lower weight to ambiguous or uncertain regions in the loss function. And then we minimize this objective in order to predict the final parameters for all the convolutional layers. Let's now take a closer look at the online learner component. So first of all, we can easily generalize this objective to include multiple reference samples. This we simply do by adding one term for each sample in our memory. Okay, then we now want to apply the steepest descent algorithm to optimize this online. And here I will actually show you the full algorithm. So it can be written in 3 simple steps that are easy to implement in, say, PyTorch or TensorFlow. Okay, so for each iteration, first we compute the gradient of this objective. And this we can implement by some transpose convolutions, otherwise it's just multiplication, standard convolutions, and so on. So quite simple stuff. Next we compute the optimal step length. This is also very simple standard operations that can be implemented in essentially one line of PyTorch code. And lastly, we update the current filters by taking a step in the gradient direction. So these 3 lines is essentially all you need to implement, to explicitly implement the steepest descent algorithm for this specific objective. Okay, now when we have covered the online learner, let's look at the full inference pipeline. So, as I described, we take the initial reference image and annotated mask as input. So the image goes into the feature encoder, the mask goes into the label generator and the weight predictor. All of these are then input to our online learner, which I described in the previous slide. So after the optimization, the output of the online learner are these weights, which in our formulation corresponds to a model of the target appearance. And given a test frame, we then apply, so this is a future frame in the video, we extract features again, and then we apply these learned weights. And we get our coarse segmentation output, which corresponds to an encoding of our the mask we want to predict. Then this, together with shallow features from the test frame, is fed into our segmentation decoder, which gives us the final segmentation prediction. Importantly, we can also very easily update our internal model during inference. So this we simply do by adding the predicted mask and its corresponding test frame to our internal memory. And this gives us another term in our online learning loss. We run a few more steepest descent iterations to update the filters and then do the prediction on a new frame. So this allows us to effectively adapt to new appearance changes. We always keep the model up to date. We can also easily train our network on a large-scale annotated dataset. On a training pair, we simply apply our network as is and add a loss between the final prediction on the test frame and the corresponding ground truth. Now let's look at some results. So the first version here only utilizes a single channel mask as encoding for our internal learner or our online learner. So this corresponds to the first version I showed you. Then here we integrate the label generator module, which leads to a substantial performance boost. So we can capture a much richer encoding of our mask using this label generator. Also, the weight predictor has a substantial impact on performance. Next are some results compared to state of the art. So here we compare to STM, which was then the main competitor, which is an attention-based approach. So we achieve a large improvement on the U2VOS dataset in particular, which is the large-scale dataset in video object segmentation. So interestingly, another benefit of our approach is that it requires much less training data. So compared to STM, which needs very complicated data augmentation strategies and additional data, if we only train on U2VOS, we outperform it with an incredible large margin. Finally, we can look at some visual results. So if you're interested in the code or models, they also exist on the PyTracking repository, where we also collect all our tracking approaches. But it actually also supports video object segmentation, so you'll also see our VOS approaches, including learning what to learn there. Next, I will briefly introduce a follow-up work that we present here in ICCV. It is called Generating Mask from Boxes by Mining Spatiotemporal Consistencies in Videos. In this work, we address the task of predicting a segmentation mask given an input bounding box. So why would we like to do that? Well, first of all, bounding boxes are very cheap to annotate compared to segmentation masks. And we also have very large scale, especially video datasets that are annotated with bounding boxes. So if we could convert these to segmentation masks, we could produce segmentation annotated datasets which we could then use to train our video object segmentation or video instance segmentation approaches in a kind of weakly supervised way. But this application itself also has or this task itself also has important applications. For instance, if you want to do interactive video segmentation where the user gives a bounding box. You can of course try to solve this problem by only considering single images. So then you solely have one input image and the bounding box, and you want to predict the segmentation mask. But this is actually a very challenging problem, because the network has to figure out the segmentation mask solely based on object priors. And as you can see in this example, it's not so easy in many cases, especially when you have a cluttered background, which is often the case in interesting videos and datasets. However, in our approach, we want to be able to utilize video, and note that if we have video, we can also exploit temporal cues. So for instance, this object is actually moving, right? So the background within the bounding box changes across frames. This means that we can look for consistency. So the consistent regions that are inside the bounding box are more likely to be part of the object that we want to segment, and the inconsistent regions, so the regions that change from frame to frame, are more likely to be background. And in fact, our approach achieves a much better segmentation on this particular example. So next I will introduce our approach. So we start from several input images and corresponding bounding box annotations. We first extract some features. We have an object encoder that I will come back to. Where the magic really happens is in our spatiotemporal aggregation module. So what does that do? So in fact, this solves an objective very similar to the one I presented previously for the learning what to learn method. So here we have our input image features X. Note that Y here is now only a bounding box. So previously it was the full segmentation of the object, but here we only have the bounding box. So what we do is to feed in both the image features along with the box into these networks E and W, which are inside the object encoder. So the object encoder gives us the label encoding and the weighting of the objective, as we saw in learning what to learn. And then we simply solve this objective using the same approach or the same algorithm, the steepest descent algorithm as we saw in the previous learning what to learn method. So note that there are some very important and interesting differences here though. So first of all, note that in contrast to the learning what to learn I presented previously, we are not given the segmentation mask of the training or reference frames. We only have the bounding box. So this is one important thing. The other, even more important difference, I would say, is that the frames we're doing prediction on, so the query frames in a sense, are also included in this optimization objective. So if we think of this as a few-shot learning problem, what the spatial temporal aggregation module does is both inductive and transductive reasoning. So the aggregation module simultaneously look at other frames and the frame if we want to make prediction on itself in order to find consistencies and inconsistencies within the bounding box region in order to then predict the final encoding, which is then decoded by our decoding module here. So here are some visual results. So especially we see in very complicated scenarios where it's extremely difficult from a single image to construct a segmentation mask given only the bounding box, our approach achieves a much better segmentation. So some first results compared to the single image baseline, we first obtained large improvement by including our spatial temporal aggregation module. What I didn't present is that we also have a second iteration where we have a second spatial temporal aggregation module that uses the prediction of, or uses our first prediction as input, and we can do a second step refinement of the segmentation mask, which is also give us some additional mask accuracy. As the main evaluation of our approach, we split the UTVOS training set into two parts. So the first set contains the ground truth mask annotations. So here we preserve the ground truth mask annotations. For the second set, which is the larger one, we only utilize box annotations. So we convert the mask to bounding box annotations. And here we see a comparison to some different methods. So only A means only training on the fully annotated data set. We compare with the recent competitor that proposed a weekly supervised loss. This is our approach, which achieves a big improvement compared to previous and is even quite close to full supervision. So one of the initial motivations of this work was that we wanted to make video object segmentation methods also work on the tracking dataset, so in the tracking domain. And these two domains are quite different. So the tracking videos contains much additional challenges such as small objects, longer occlusions, longer sequences, so you need to be much more robust and so on. So what we did here concretely was to, with our automatic approach our network represented previously, annotate the Lassot and the GOT10K training data sets with masks, and then we fine-tune the learning what to learn model that I presented previously on these data sets. One of the data sets we then evaluated on is the VOT 2020. So what is good with this data set is that it in fact has mask annotations while still being a tracking data set. So compared to the baseline learning what to learn, we achieve a very big improvement and is even very competitive with the winner on this challenge, which is very specifically designed for this task. Lastly, I will present Learning Target Candidate Association to keep track of what not to track that we presented here in ICCV. One of the main open challenges in tracking right now is the handling of distractor objects. So while we partially address that using these discriminative appearance-based methods I presented, the problem is that distractors can have more or less identical appearance to the target object that we want to track. So even with a discriminative model, you encounter circumstances where appearance is simply not enough. You have to rely on additional cues. And as you for instance see in this sequence, even the dim tracker that I presented earlier incorrectly assigns a higher tracking score on the distractor object, which causes tracking failure. So the annoying thing is that distractors are actually very, very common in natural tracking applications, because similar objects often co-occur. If I'm interested in tracking some particular object, I have to deal with that there might be similar objects around. So to address this common problem, we propose to keep track of distractor objects. From an appearance-based tracker, we use a score map to detect target candidates. So the set of target candidates contains not only the target, but also possible distractor objects. So now we have simplified the problem into selecting the correct candidate as our target object. To solve this problem, we propose to use the previous frame and its target prediction. Our idea is then to match the previously predicted target in order to select the best fitting candidates. However, we do not only match the target from the previous frame. Importantly, we also match all previously detected distractor objects from the previous frame to the current frame. By matching distractors, we eliminate potential matches for the target object. And this greatly simplifies the problem of matching the previously detected target object to the current frame. In order to predict the assignment of candidates between frames, we extract a set of features. So first we use the score value produced by the tracker. We also use appearance features extracted by the backbone network. Finally, we use the spatial location of each target candidate in the frame. After extracting the features, we encode them into a single feature vector. Then we enhance these features using a graph neural network consisting of self and cross-attention layers. This enables the exchange of information between candidates in the same or neighboring frames. And finally, we feed these refined features into the optimal matching module that predicts the assignment probabilities across the candidates in the two frames. To train the proposed association network, we require annotations for the target and distractor objects. However, most generic object tracking datasets provide only a single annotation of the target object. Hence, we can only use annotations for partial supervision of our model. Namely, we supervise only the association of the target object between frames. In addition, we make use of self-supervision to learn distractor associations. We enable this by synthetically creating the features of the previous frame by augmenting all extracted features from the current frame. In this scenario, the assignment between distractors across frame is known, which allows us to achieve full supervision between such a pair of frames. During inference, we keep track of distractor objects over the full sequence by assigning a unique object ID to each detected object. Then we use the predicted assignment probabilities to propagate these IDs from frame to frame. This directly enables matching of the target and distractor objects between frames. In addition, we assign a new object ID to each object that does not match with any object in the previous frame. Our tracker is able to match distractors and a target object across frames. Our tracker keep track is robust to distractors and keep tracking the target object even in cluttered scenes, or when the target undergoes partial or full occlusion, or when a strong distractor appears. When comparing Keep Track with the baseline tracker SuperDimp, we observe that Keep Track gets less confused by distractors and keep tracking the target for cases where SuperDimp fails. Keep Track sets a new state-of-the-art result on 6 benchmark datasets. In particular, it outperforms previous approaches on the very long-term and challenging LaSOT and UAV datasets. Moreover, Keep Track outperforms recent trackers on the long-term dataset OXUVA and VOT LT19. To conclude, I first talked about the effectiveness of these discriminative learning modules for end-to-end tracking. Then we want to generalize these modules and show that they can perform or can act as a general layer for non-local reasoning also in other applications such as video object segmentation and weakly supervised video segmentation. We explored going towards robust video object segmentation in the tracking domain. And lastly, we tackled one of the biggest remaining issues in visual tracking, namely distractors. I particularly also want to thank the other first authors in the works that I presented here, Gautam at ETH Zurich, also Christoph at ETH, and Felix at Linköping University. If you're interested in visual tracking, I also want to say that we're organizing the visual object tracking workshop here at ICCV. It contains 4 challenges, one on short-term tracking, where, as I said, we have segmentation ground truth. We have one for real-time tracking, one for long-term, and one for exploiting both color and depth information. Lastly, I want to mention that all the works that I presented here are implemented in our PyTracking repository. We have worked on this repository for over 2.5 years, and it has received some quite substantial interest. So in addition to these implemented works, you'll also find very good tools for training and evaluating your tracker. So we have integrated all common datasets. We have loaders, metrics, analysis, and other general building blocks for building your own tracker. Okay, thank you very much for your attention.